We are really excited to have our every Wednesday science class with Miss Anna from Michigan. And today we're going to talk about at-home science, but these are going to be completely different experiments than we did way back in March when we were only supposed to be doing this for 2 weeks. Someone reminded me yesterday that we were just doing an experiment for 2 weeks, and here we are going into week 12 next week. So we're excited to connect with Miss Anna. I would, boys and girls, as she's going through the program, I would be jotting down the materials that you can use from your home to do these projects with mom and dad, maybe, and your brothers and sisters, maybe a little later. So I'm going to turn it over to Miss Anna, and we're going to have some magic and science and things that we can do at home. So over to you, Miss Anna.
Thank you. So hi, everybody. Thanks so much for joining. I love seeing everybody, all these familiar faces. I really do feel like I'm getting to know you just like Molly and Katie do every single week. So thank you for tuning back in. Like Molly said, today we've got all sorts of activities that you can try at home. Now, I tried to pick some materials that are really, really easy this time. So most of these materials, you probably don't even need to go out and buy anything for these experiments, because these experiments are all about water. So we all probably have water either running in our house, or hopefully maybe you have water outside your house somewhere. So all of these experiments we can do with water. We're going to talk about the different properties of water and how we can actually use it to do some pretty amazing science tricks. And they might seem like magic, and I'm hoping that you feel that way, because maybe your friends and your family might think that these are magic tricks, but you will get to know the science behind them, which is going to make it really, really cool. You can show off these tricks to your friends, and then you can share the science with them so that they can spread it all around. So the first challenge, or the first science trick, I want you guys to think about this one with me. So the challenge that I'm going to try to accomplish with my big bin of bright blue water. So this is just water in the bin. I put some drops of blue food coloring inside here because I think everything is more fun when it is colorful. You don't need to use food coloring for this experiment, but I did because I think it makes it look really cool. So big bin of blue water. And then I also have a piece of construction paper here. This is just a regular piece of pink construction paper. And this is the challenge that I want us to figure out together. Do you think there's a way for me to take this piece of construction paper and hold it under the water for 10 seconds without getting it wet? What do you think? Think about this. Do you think that's possible? Maybe we start with that side. Do you think it's possible to hold this piece of paper under the water for 10 seconds and have it stay completely dry? What do you think? Is it possible? Yes or no? A couple people unsure. May thinks yes. So does Aubrey. Erin says no way, right? Because paper is super absorbent. Braille says probably. So why else would I pull or propose this challenge, right? If I didn't have at least an idea of how we might accomplish this. But if you're saying no, that makes a lot of sense. I understand why you say no, because paper is really absorbent, right? As soon as paper comes in any contact with water, it absorbs the water. The water wants to go from an area where there's lots of water to an area where there's no water, like inside our paper here. Paper has all these little pores inside it, and so it will absorb the water through what we call capillary action. Anton is like, no way, of course not. A couple people giving me some suggestions for how we might manipulate this experiment so that it's possible. Gabby has a great suggestion that we could cover it in wax. I do have a candle here, but I have a different solution. So let's start with solution number one. And I'm not sure what you guys will think about this one, but again, the challenge is just to hold the paper underwater for 10 whole seconds and keeping it completely dry. So here's my first solution to this problem. What do you think if I were to just do this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, what'd you think about that? Totally dry, right? But that wasn't very cool or exciting, and it didn't use a whole lot of science. So if you are kind of doing one of these right now, I completely understand. That wasn't very cool or exciting, but it is one workaround around the trick, right? It was under the water, But like Gabby said, and Aaron both are telling me I cheated. I'll agree, that wasn't the fairest solution to the problem. Maybe a little bit deceiving in the question. But I do have another way for us to do this. So I do need another tool, and it's not wax. For this, all I need is an empty glass. Any empty glass would work for this experiment. I chose a clear one. That way you can all see through it, and you can actually watch this experiment take place. So what we need to do is we just need to crumple up our piece of paper, not too tight, but just small enough that I can actually fit it here inside my empty glass. So the glass is dry on the inside and the outside right now. And then all we're going to do is we are going to submerge the glass with the paper in it and hold it underwater for 10 seconds. But if I hold it right side up, right, you might know that the water is going to immediately rush inside and it's going to get the paper wet. So that wouldn't be so great for our challenge. But instead, we're going to flip the glass upside down. And maybe this is something you've tried before, either in a pool, if you've ever swam in a pool before and had something like a cup with you, or maybe even in the bathtub. This is super easy to try, something we are pretty familiar with, but we're going to talk about the science behind it. So let's go ahead and, like we said, we're going to hold the glass directly upside down, not to the side and not right side up, completely upside down. And basically we're going to trap an air bubble here inside this glass, and let's hold it underwater for 10 seconds. Here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, carefully, right? Because we said we don't want to tip the glass and allow water to get inside. I can see from my view that we still have a big air bubble trapped inside there. So we want to carefully take our glass out of the water very, very slowly. And then it might also be helpful, I had a towel around here somewhere, just to dry off the outside so that when we take the paper out, we're sure that none of those drips of water from the outside of the glass get on our piece of paper when we check how dry it is. So let's go ahead. I'm going to pull out my piece of paper, dry off my hand, and let's open it back up. And we will see that our paper is still totally, completely dry. That worked, right? And a couple people saying that they've done this before. So this is a very easy challenge that you could show your friends, and maybe they also don't think it's possible to hold the water or hold the paper underwater for 10 seconds, but now we know it is. So let's think about why this happened, right? There are a couple factors at play when we take a glass and we put it upside down inside a bin or a bathtub or a pool, right? We're trapping a big bubble of air inside the glass. We need to think about air pressure. And air pressure is all around us. We've mentioned this in the past in some of our sessions. Does anyone remember how many pounds per square inch of your body are pushing on you all the time? If you don't remember, does anyone want to take a guess? We measure air pressure, the actual force of air pushing on things. We measure it in pounds per square inch. So how much weight per every square inch of an object is pushing down just from the air around us? Whoa, some big numbers coming in the chat. Think a little smaller. Think about how many pounds per square inch your body could possibly handle, right, of air pushing down on you. Charlotte and Isaiah guessed 50. We're getting closer. May says 100. That's still a little too high. C is the closest one so far, who says 20 pounds per square inch. Aaron says 1. Think a little higher than 1. 30. These are great guesses, everybody. We are definitely honing in on that range. But there's actually about 14.7 pounds per square inch of air pushing on your body. So think about a square inch. That's about the size of a quarter. So imagine a quarter, and then imagine a 14.7 pound weight. That could be like a really big bowling ball. Imagine the weight from that bowling ball pushing on something the size of a quarter. For every quarter-sized piece of your body, there is a bowling ball pushing down on it from the air. But we actually can't feel it. We don't feel air pressure, and that's good, right? Because 15 pounds for every square inch of our body, that's a lot of air pressure, right? But we don't feel it because there is an equal amount of air pressure inside our body as there is outside their body. And so Charlotte and Isaiah say even babies can lift 14 pounds. That's technically true. Just using the air from inside your body, you're not necessarily lifting it, right? But you are at least resisting it, keeping it from crushing you because of that equal amount of air inside versus outside your body. The same thing is happening with our upside down water glass trick. When we trap that air bubble inside, right? Obviously, the water wants to rush inside the glass. It wants to fill the glass with water, but there are 14.7 pounds per square inch of air pushing outward, pushing on the water and kind of keeping it out of the way. Now, there's air pressure, right, pushing down on the bin of water too. So on the surface of the water, there's 14.7 pounds per square inch, but there's an equal amount of pressure inside the glass. And so as long as we hold the glass straight up and down, so as long as we don't tilt it to the side to cause an imbalance in pressure, we can actually resist that force of air pressure that's pushing the water up into the glass. But there's another trick we can try with this, another one that maybe you've tried at home, but it is one of my favorite science experiments that I think people actually discover on their own, which is pretty amazing because even when we're really, really little kids, even babies, and we are in the bathtub, maybe you've tried this trick before. So this time I'm actually going to fill the glass with water. We're going to fill it to the very tippy top. I'm going to flip it back upside down so it's full of water now. There's no air inside the glass. And then I'm just going to lift up on it. And I want you to take a close look. So let me zoom in on our bin here. And now I'm going to lift up on the glass. And can you see that the glass is full of water? We're actually lifting or pulling the water out inside the glass from the bin, right? That's because this time there was no air inside the glass to push back on the water. We've created an area of really low pressure here inside the glass, which is allowing the air pressure from outside the bin, right, to hold the water. When we talk about forces or when we talk about interactions here on Earth, we say that there are four major interactions between atoms and molecules and particles. The weakest one of all of these is that same interaction that keeps our 2 feet on the ground. It keeps us from floating away. What interaction or what force am I talking about? I'll give you another hint. It's the same force that's trying its best to pull the water down out of the glass. What force or what interaction am I talking about? Yeah, lots of people guessing it, right? Think about what's keeping us from floating away from Earth. What's keeping or what's pulling down on the water, wanting the water to fall back into the bin? That's right, it is gravity. You guys are so smart. You've learned so much, I can tell, over all these sessions. So gravity is pulling down its hardest on the liquid inside the glass. It has weight, right? Water is actually very, very heavy. And so the water is being pulled down by gravity. But we say that out of those four major forces, that gravity is actually the weakest one. It's not very strong at all. So even the force of air pressure is stronger than the force of gravity, which keeps the water inside the glass. We can try this with a larger glass too. So I've got a little bit of a taller glass here. So let's do the same thing. Fill it with the water. So you can see I'm tilting it to the side just to get our water totally full inside the glass. We're then going to pick it up so we can see that already we've got some water out of the glass here. And then we just carefully lift up. So even with a taller glass, still, so there's much more water in this cup, right, than there was in this one. So there's much more weight from this water. But even with more weight, the force of air pressure pushing down on the water is still stronger than gravity. Gabby asked a good question asking about gravity. So how does gravity keep us from floating away? How does it keep us here on Earth, right? And gravity is an interaction between anything that has mass, anything that's made up of matter. We are made of matter, and so is the Earth, and so is water. But the thing with the most mass, the heaviest object, has the most gravity, and so you'll be attracted to anything larger than you. Obviously, the Earth is the largest thing we come in contact with, and so we all stay here on the ground. Gravity works kind of like a force that bends space-time and causes everything else in the universe to kind of gravitate or pull towards it? Good question. Gravity is very, very complicated, but we can talk more about gravity. I could talk about gravity all day, but it's still something that we don't totally understand. We know a lot about gravity, but since it's something we can't actually see, it's one of those things that we call a theory. We can't actually prove gravity because it's not something tactic. It's not something that we can touch or see, but we can see how it interacts with things around it, which is why we don't usually call it a force. We might have heard it called a force, but the real term that we should call gravity is an interaction. Now, if I lift up the glass higher than the seal on the bottom of the glass, right, the water pours right out. So as soon as we kind of break that seal, right, as soon as we break the seal, that force of gravity then becomes stronger than the force of air pressure, and our water rushes out towards the bottom. Now, there is a limit to this, right? So eventually, with enough weight inside the glass, gravity will be stronger than air pressure. But there's been lots of studies done on this, and the height or the distance that we would need to pull a glass like this out of water to get enough weight to get the water to pour out of the glass, even without lifting it, is about 10 meters. So it's a huge amount of water. It's very, very heavy and way too much. It's way too tall for me to do here inside my studio. So we can't do that experiment here. But this is a really easy experiment for you to try at home. Now, I have another experiment, or actually another way we could just set up this same experiment. May ask a great question. Can you use a plastic cup instead of a glass cup? Yes. I like to use a clear cup because you can actually see the water inside them, but you can use any sort of vessel, anything that has a flat top on it. So if you have a cup or a bucket or a pitcher, any sort of plastic, glass, container. Paper probably doesn't work too well because we said that paper is really absorbent. It might work for a little while until your cup gets really soggy and actually will kind of lose its shape and be hard to hold on to. So try it with all different sorts of vessels. You can take cool pictures and make sure you send those to Molly and Katie so that I can see that you guys are trying some of these experiments at home. Now I've got another experiment set up using this candle over here to the side. Let me see if I can get a little bit of a closer view. There we go. So we've got a shallow pool of that blue water here inside this tray. So there's some water on the tray. And what we're going to do is we are going to light this candle. Now, this is another experiment you can try at home. And this is actually just another way for you to try to accomplish that same experiment, trying to suck the water up into the glass. Now for this, we have to talk about those movements of atoms and molecules, which you know if you've tuned into my past sessions, I love to talk about atoms and molecules and how by adding or taking away heat, they move differently, right? So we've talked before about when we get atoms or molecules very, very warm, they start to have more energy. So they start to move around more quickly, and they also start to spread out and take up more and more and more space the warmer they get. But the opposite happens right when we cool them back down. When we cool atoms and molecules back down, they lose their energy. They start to move slower, just like you or I might move a little slower when we're really, really cold. So those molecules will move slower and they'll also contract or take up less space. And May remembers that we talked about this during vacuum science. That's exactly right. So we are going to try to form a vacuum here inside this glass cup. Now for this, since we're using our candle, I want to make sure I get my cup nice and dry. And let's go ahead and take a look over at our candle. Now the first thing I'm going to do is I'm just going to hold the glass over the candle, which is going to allow me to start warming up those air molecules inside. You might see a little bit of fog starting to form on the glass. It's not going to get super hot, but basically right now we're just warming up those molecules inside the cup, causing them to take up more space. Now candles rely on fire, right? Or a combustion reaction, which is another thing we've talked about here on Echo Live or on our sessions here with Echo. We know that fire needs fuel, heat, and oxygen in order to take place. So when we hold the glass over the candle, right, eventually that reaction runs out of oxygen. And so our candle goes out. And then what do you notice inside the bottom of the glass? Do you notice anything happen down here at the bottom? Did we get a vacuum or did we create any suction? Right, Gabby sees water up in the glass. So we've pulled some water out of the tray, right? Because we've created a vacuum here inside this space. Once the candle went out, right, we lost our source of heat, which allowed those molecules of air inside to cool back down. So the colder they get, right, the less space they start to take up. And so they left behind a good amount of empty space here inside the glass, which then caused our candle to go out and our water to be pulled up into the glass in order to fill that empty space. Now, we can do this on a larger scale. Now, this one is not necessarily something that would be easy to recreate at home, but I did want to just show this one to you. So this one I might not recommend trying at home. You could, but it takes a couple large-scale materials, things that you might not necessarily have or easily be able to recreate, but I'll explain it to you just in case you have a parent or an adult that's willing to help you with this one. We're going to do the same thing. We're going to create a vacuum using this hot and cold science, but this time we're going to do it here inside this big empty glass bottle. So this is an empty glass bottle, but I've taken the lid, and the most important thing about this experiment is I've taken the lid, let's see if I can zoom in, that's not the one we want this one. I've taken the lid and I've poked a hole through the top and then just put a plastic drinking straw through it and glued it in place. So if we're going to create a vacuum, right, the first thing we need to do is heat up these molecules of air inside the glass bottle. We're going to do that using some boiling hot water. I know someone told me it was a little blurry. I keep focusing my camera, but I'm not having good luck with that. So let me know if it's too blurry, and I can keep focusing if necessary. But we said we're going to fill this with boiling hot water, which is going to cause those molecules to expand, right? So make sure I get my water nice and hot, and then what we're going to do is we're going to dump out the water, only leaving behind that really, really hot air inside the glass. We'll then quickly put on our lid, screw it all the way tight, and then submerge the top of our bottle down inside this really, really cold ice water. When we do that, right, we're going to cool off the air inside the bottle, leaving behind empty space, which should suck the water out of the bowl, up through the straw, just like you or I would do when we're using a straw to drink. All right, let's go ahead and let's try this. We've got our electric kettle here, full of really, really hot water. Carefully fill our glass bottle all the way to the very, very tippy top, because we want the whole bottle, even the glass, but especially the air that's going to be left behind once it's totally full. We want that to get really, really hot. So we'll give it just a second here to warm up the bottle. Of course, I have a glove here because that's boiling hot water. So if I were to touch this glass like I need to do in order to dump the boiling water back out, it could burn me. And so always better safe than sorry. And safety is always our #1 priority when we're doing science. So like we said, quickly place our lid back on the bottle and then put our bottle inside. Now, what did we see? It really worked, right? We created a massive amount of empty space, which we can actually see now with this really, really full bottle of water. This represents the empty space that was left behind when we heated up and then rapidly cooled down the air inside the bottle. So you can see just how much space warm air takes up versus cold air, right? This is the amount of empty space we had left over. And so the air pressure pushing down on our bowl of ice water caused that water, right, to be pulled up into the straw to fill the empty space that we had left behind. So this one, not as easy to recreate at home. If you are interested in doing it, I'll send a materials list for every experiment that we try to Molly and Katie to publish with your resources. But this replicates the same exact thing as our candle glass over here. So they're the same science, but this one's just a little bit more difficult to recreate at home. I will send a materials list just in case you are all interested in trying these at home, which I know you might be. All right, we've got a couple more water experiments for us to try together. So let's move away from this suction type activity, but we're still going to be talking about hot and cold water. Now, there's a really, really easy way to visualize or see the movement of atoms and molecules. So not just the empty space that they leave behind, but I want you guys to actually be able to see this movement of atoms and molecules in hot or cold substances, because we talk about it on Echo Live all the time. And so I figured we should probably take a look and actually prove it to ourselves just how fast these atoms and molecules move when we're talking about something that's either very, very hot or very, very cold. So we need two things for this. We need a few things for this. We've got two empty glass beakers. Again, clear cups or clear containers work best for this. They don't have to be glass, they could be plastic. And so in this container, I have cold water. We'll pour some cold water into our first beaker. And then we'll take a little bit more of our hot water from our tea kettle and pour it in the other glass. Now, when we talk about hot and cold, if we were talking about temperature of water, which color, in your mind, which color would you say is red or blue should represent hot? Should red or blue represent hot? Tell me what you think in the chat. Red or blue, red or blue, red or blue to signify hot water. Yeah, everyone picking red. But I figured this is a fun time to talk about one other kind of science, because why not? But when we talk in science, we're kind of mad at the people who labeled the water coming out of our sinks. Because when we wash our hands, right, the red side of the sink or the red tap usually represents hot water. But in science, that's totally incorrect. We don't know why they labeled it that way. I have a guess. I would say that they might have labeled it that way because, you know, red might symbolize fire, whereas blue might symbolize ice, which is very, very cold. But if you do any experiment in science using fire, when we look at the hottest flames, when we look at flames that burn really, really hot, those flames are blue. So if we've also looked at astronomy, if we look at stars in our galaxy, but in other galaxies, the hottest stars are blue stars, whereas red stars are actually fairly cool. Our star is a yellow star, so it's somewhere in the middle, not too hot, but not too cold. So for this experiment, it might be a little confusing, but since we just learned that in science, blue represents hot, we're gonna dye our hot water blue, and we're gonna dye our cold water red. So just a fun fact for you guys all about science. It's good that we know which side of the sink represents hot and cold water, but of course we want to learn something here on Echo. And so we're going to use blue to represent hot because that is scientific. All right, so we're going to add a drop of food coloring to each beaker at the same time. And then, like we said, what we're looking for is that movement of atoms and molecules. We want to be able to see how quickly these molecules are moving. So let's go ahead and we'll do them at the same time. And then just watch carefully what happens in our two beakers. And tell me, what do you observe? What do you notice happening inside our two beakers? Remember that blue is hot. You can even see some steam starting to accumulate on the top. Blue is hot, red is cold. What do you notice? What do you observe? Tell me your observations of this experiment. Yeah, good. If you're taking a moment to think about it, that's great, right? Because our experiment is still going, even right now. But tell me what you notice. Lots of people telling us that the blue, it spread very, very quickly. The blue food coloring dissolved or diffused into the hot water much faster than our red dye did. So what is going on, right? We are observing the speed that these atoms and molecules are moving at. In our blue beaker, right, we said warm molecules have much more energy. That's what we call kinetic energy, right? Energy of movement. And so that those quickly moving water molecules are churning and mixing and swirling around, which mix that food coloring in very, very quickly. But the molecules in our cold water are moving much more slowly. They don't have a whole lot of energy, and so the food coloring is taking a lot longer. We've still got lots of clear water left in the glass, especially if I were to hold my hand up behind it, you could still see just how much clear water is left over. You can still see my fingers through it, right? You can even see colors, or if I were to hold a note behind this one, you could even read it. But you might also notice that that food coloring sank way down to the bottom. That's because these cold water molecules are moving so slowly that they're not letting the water or the food coloring mix into it almost at all. And so instead, what's happening is, since the food coloring is more dense than the water, it's just sinking down to the bottom and forming its own layer down here. Now, of course, water molecules are moving. Even when they're cold, they are moving. It's just going really, really, really slow. But eventually, right, the heat in the room is going to cause those molecules to warm up. And because of what we call diffusion, the molecules of food coloring are going to eventually spread out and fill all that space inside the glass of water. It just goes really slowly in the cold water and really quickly in the hot water. But that is good evidence, right, of the science we've talked about here on Echo Live in the past. That's a good way to observe that when molecules are warm and have lots of energy, that they move very quickly. But when we cool them down, they move much more slowly. And they're packed so tight together, just like we talked about, right, that they're not letting the food coloring mix into them. I have another really cool experiment that we can try using this exact same science. And we're going to tie this one to density. So I have 4 clear beakers here. These ones are plastic. So we said that plastic, glass, either one works for this experiment. I might recommend plastic for this experiment, and you'll find out why once we get this one started. And you'll notice that I also have my handy dandy laminated card, which you might have seen me use on a past episode or a past session with you to do our gravity fail trick, where we get water to hover over the air. But we're going to use it for something different here today. So we're going to need 2 cups that are full all the way to the top. Actually, I'm going to add my food coloring first here. So we're going to do blue is hot. So we'll put the blue water for those ones, and we'll fill those ones with hot water. And all right. And then, of course, we need 2 cups of cold water. So we're going to fill these to the very, very brim, all the way to the very tippy top, which is going to be important for this experiment. So we've got red, which represents cold, right? Red represents cold to make it just a little bit more colorful, right? And a little more blue to our blue side. And we're going to fill those ones all the way to the very, very top with hot water. All the way to the top, all the way to the top. Now, what we're going to do is, using our laminated card, we're going to try to stack these different temperatures of water on top of each other. So the card is going to help us to get to be able to flip these cups upside down without spilling it. And so I'm going to go ahead, I want to zoom in so you guys can get an up close look. Here we go. So remember, which one is the hot water? Tell me one more time in the chat, which one is the hot water? Make sure you guys are paying attention, making good observations. Oh yeah, you guys are listening. The blue water is our hot water, right? Blue represents hot, just like flames and just like stars. Someone asked, what is a laminated card? A laminated card is coated in plastic. So you can see that there's a clear layer of plastic around this card. If you have a teacher for a parent, they probably love their school's laminating machine. If you have one, I know I love the laminating machine at the Science Center. It makes it so, if just in case your paper were to get wet, like this one is about to, it's not going to absorb any water because it's coated in plastic. Laminating is super duper fun. If you ever get a chance to do it, be very careful because you have to heat things up really hot to melt the plastic to make it stick to the paper, but it is super fun. All right, so we are going to be stacking our cups of water here. The first one we are going to stack is we're going to take a cup of hot water, our blue water, and we are going to stack it on top of one of our cups of hot water. Oh, it's spilled just a little bit. I want to set those off to the side, make sure we have lots of space. But we are going to take our cup and always do this over a tray or over a sink somewhere where, just in case you do spill, because I know I'm going to spill just a little bit, you're not going to get water all over the place. So I've got our hot water on top and our blue water on bottom, and then we just want to carefully remove the card and try to leave the glasses stacked exactly on top of each other. So it takes a little bit of patience here. But take a look at that. Look what's happening to our two layers of water, right? They're staying completely separate, and that is because of their density. If you remember, our food coloring sinking down to the bottom of our cold glass of water, right? When things are cold, those molecules are very, very tightly packed together. They're denser, they're heavier than the warm water. So since the cold water is much denser or colder than the hot water basically floats on top. And so those two layers stay almost completely separate. Now let's go ahead and we'll try stacking them in the opposite direction. So this time we're going to take the cold water, the really, really dense cold water, and we're going to try to stack this cup on top of the hot water. And I want you to tell me, what do you think is going to happen when we do that? I'm going to fill this one all the way back to the tippy top. That way our two experiments are exactly the same except for the orientation of our water. What do you think might happen in this one? We'll go ahead and we're going to take our cold water, our red star or our red water is the cold water, flip it upside down, balance it on top. You can see that I'm spilling just a little bit, which is why we always do it over a tray, just for a little bit easier cleanup. Now, let's see, what did you guys think? So before I remove the card, let's take a look. Ooh. Gabby told me if I did it the other way, the bottom is going to mix. Red and blue is going to mix. Some people are even talking about color theory, so you must be learning a lot about art from your Connected North sessions as well. That color theory would tell us that if these two cups of water do mix, like a lot of you are predicting, that we might get purple water because red and blue make purple, which is a secondary color. Awesome job. All right. Lots of people telling me that they are going to mix. Let's go ahead and test it out. Let's see if you guys are right. Whoa, right? Almost immediately, our two glasses of or colors of water have mixed to form a purple mixture, a really, really dark purple at that, since I added so much food coloring to these glasses. This is a really easy experiment, right? And what was different in this one is that we stacked them the wrong way. Instead of putting the light one on top, the one that's going to float, we put it on the bottom. So we put the heavier or denser red water on top, which immediately wanted to sink. It wanted to push down to the bottom because it's so much heavier. And so it pushed down, causing all of those molecules to mix together very, very quickly, giving us a purple mixture, right? So what do you think about this one, though? Our separate glasses of water. Do you think it'll stay like this forever? What do you think? So this one mixed very, very quickly. Or when we stacked them the wrong way, or we don't want to call it the wrong way, but I guess when we stacked them heavy on top and light on the bottom, they mixed really quickly. But do you think this one will stay like this forever? A lot of people say yes, no. If you say no, can you tell me why not? Why don't you think these will stay like this forever? What might stop them from staying like this? The water could evaporate. That's a very good thought. The water could evaporate. That might take a really long time because right now the glasses are stacked on top of each other very, very tightly, and so not a lot of air is getting into the glass. Yeah, a lot of people say that eventually over time, right, the hot water is going to cool down as it loses some of its heat to the environment around it. We're going to lose some of that heat, right? It's going to dissipate into the air. So we'll lose some of that heat, but the cold water will do the opposite, right? The cold water is actually going to heat up because it's actually going to absorb heat from the air around it. So over time, these two cups of water will become the same temperature, which is going to allow them to mix much more easily. If you try this one at home, though, a really cool experiment that you could try is as soon as you flip them over and leave them separate like this, start a timer either on your phone or on your stove, or just make a note of the time and keep checking back on it. Once you see them mixed together, note how long it took. That will depend, right, on the temperature that your water started at. So I have my cold water in the fridge, but if yours started even colder, maybe even like ice water, it could take longer. I had really, really hot water on top, but maybe if you only choose to use warm water from the tap, yours could take less time. But that is a really good experiment, right? Actually measuring your data that you get that you can try at home. So again, I'll try this at home science, and so far really all we've used are some cups, some water, and a candle. So all really easy and really, really fun experiments. Now I've got one last thing I want to talk about using water. This one, you might not have these exact materials at home, but I do have a suggestion for how you could recreate this and turn it into your own type of experiment. Now, I'm going to set my big bin of blue water way off to the side where it's not in my way, because I want to talk about something that we call thermal conductivity. Thermal conductivity has a lot to do with what we just talked about water either cooling down or heating up, and how easily that process happens. So thermal conductivity means how quickly or how well you can absorb heat or transfer heat from the environment or from things around you. So I've got two blocks here. I've got two black blocks, but they're made out of different materials. So this one right here, this is an aluminum block. So aluminum is made out of metal, or it's a type of metal. So you can almost hear it, I bet, if I tap on it. Sounds like metal. This one is aluminum, where this one, even though it looks very similar, this is what we call a high density foam. So it's almost like a plastic, but a really, really hard plastic. And so they feel kind of different to the touch. So there's an experiment that you can try with me right now, really quickly in your home. Look around the room, find something that is metal, maybe like a doorknob, or if you have a metal chair near you, go ahead and touch that piece of metal and make an observation. Think about how it feels in your mind. So I'll give you guys, I'll give you 10 seconds to find anything of metal. If you have something aluminum, that's even better. So 10 seconds to go touch something metal and make an observation. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. All right, if you have an observation about how it feels, you can tell me in the chat. Charlotte and Isaiah said that they touched a spoon and it was very, very cold. That's a great observation. Now, I want you to look around your house and find something that's made of plastic. So find something made of plastic, or if you don't have plastic, this is designed to act like wood. You can find something made of wood instead. So now you have 10 seconds to touch something that's made of plastic or wood, and make an observation about that. So I'll give you another countdown. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. All right, now if you had to compare, think in your mind about how those two things felt differently. Really just think about those. Did anyone else notice that the metal object probably felt much colder than your wood or plastic object? Do you agree or disagree with that statement? I'm asking, did you notice that the metal was colder than the wood or the plastic? Tell me if you yes agree or no disagree. All right, most people are agreeing that the metal object they touched was much, much colder. May says disagree, which is okay. Maybe it depends on the type of metal or the type of object you touch. So you might have had an opposite experiment. But of course, I have my two variables here, my aluminum and my high density foam, and we're going to take a temperature reading on these two materials. So I have this device right here, which is an infrared thermometer. Infrared is a type of light that we've talked about during our visible light episode. So we can't see infrared, but infrared can actually bounce off of objects, bounce back to my sensor here, and tell me what temperature these objects are. So let's take a temperature reading. All right, so our aluminum block, the metal, that one is about 70.2 degrees Fahrenheit. Or if I switch this to Celsius, that's about 21.3 degrees Celsius for our aluminum block, and that's about room temperature here in my studio. The plastic, or the high density foam, is about 22.1, so almost a degree warmer for my foam block, which sounds about right for what you guys told me in your room too. That metal feels just a tad colder than plastic does. Now here's the experiment we're going to try using our two black blocks. Now I have these plastic rings, which are just going to allow me to hold something in place on top of our blocks here. So I'm going to take a piece of ice, or an ice cube, and I'm going to place an ice cube on each of the blocks. Before I do that, based on what we've learned so far, that we have a cold aluminum block and a slightly warmer density foam block, which one do you think is going to melt an ice cube faster? So tell me what you think in the chat. Is it the metal or the foam? Which one will melt an ice cube fastest? Go ahead and tell me in the chat. So, foam, plastic, okay. A couple people saying metal, a couple people saying plastic. These are great hypotheses, you guys. You're really thinking about the variables of our experiment. So maybe you know, right? That, or maybe you're thinking that, there we go. Break up my ice cubes here. So let's go ahead and let's take one ice cube and place it on each tray. All right, so we've got two identical ice cubes here, and let's just make some observations. Let's just observe our experiment. So remember that this one is the metal, or the aluminum, and this one is the foam. What do you notice happening? I can even see results happening right before our very eyes. Yeah, lots of people observing that the cube is moving all over the place here on our aluminum, or our metal block, but the one over here on the plastic, or the foam, is not moving at all. This one is rapidly shrinking down in size. We are melting that block, or that ice cube, very, very quickly, whereas this one is pretty much entirely. Let's see if I can get my camera to focus here. There we go. Wow, look at that, right? Now remember, this block started off much colder, or about a whole degree colder than our plastic block. But let's take a new temperature reading. So let's take a temperature reading now. Now, our aluminum block, now that we've set that ice cube down on it, is about 15 degrees Celsius. And our plastic, or foam block, is about 20 degrees Celsius. So now this one is 5 degrees colder. So what is going on? How is it possible that the colder block is melting the ice cube faster than the warmer block? We normally think about warm, right, being able to change those states of matter very quickly, right? By adding heat, we should be melting this ice cube. But let's see, like Charlotte and Isaiah said, we are talking about thermal conductivity. Thermal conductivity works just like electrical conductivity. If something is really conductive, it allows electricity to pass through it very quickly. If something is thermally conductive, it allows heat to go through it very, very quickly. So even though the aluminum block feels very cold, that's because it's transferring the heat from the air through the block and up into the ice cube. the thermal conductivity of plastic, like our high density foam, is really, really low. It doesn't really allow for that movement of heat energy, and so it's not transferring any heat to the ice cube. The ice cube is only melting at the rate that it's interacting with the heat in the air. So it goes really, really quickly. If I could even add another ice cube to our aluminum tray or our aluminum block, and we'd probably melt maybe even 5 ice cubes before this one even came close to melting. And that's again just because of the thermal conductivity of this block. Because it's transferring all that heat from the air, actually the colder the block gets, right? The colder it gets from touching the ice, the more it wants to absorb heat from the air and then just transfer it right back into that ice cube to be melted. So let's take one more temperature reading of our blocks here. Now we're at about 12.9 degrees Celsius for our aluminum block. So we've dropped a whole 10 degrees almost from our starting temperature. And the high density foam block at 19.9. And so we've dropped about 2 degrees on this side, and we've dropped almost 10 degrees on this side because aluminum is much more thermally conductive than the high density foam. I do have this measurement tool here, so this is a pretty fun measurement tool. So this actually is just 4 different metal strips, so 4 different types of metal, and they each have one of these little color changing thermometers on it. And so right now the little blocks on our color changing thermometer, they're all black, but once they start to conduct heat from the metal, they'll start to turn green. So let's take a look at that. We can actually do it with a glass of that boiling water. So one more glass of boiling water here, pour it right here inside my glass. And then we're not going to submerge the actual thermometers. We don't want to submerge this part. All we're looking for is how well these different types of metal will conduct the heat from the hot water. And so the 4 metals on here are, the bottom is steel. The next one up, this one is brass. Then we have aluminum, which is the same stuff that our block was made out of. And then on the very top, we have copper, which we might normally find in the pipes inside our home. So let's go ahead and I'm going to just submerge. Let me turn my camera just a little bit. I'm going to submerge them in there. We'll give them just a moment to start conducting that thermal energy from the water. So remember, I'm not submerging the thermometers, just the ends of the metal down into the glass. And then we'll zoom in and take a closer look at this so you guys can actually see the temperature reading once we get some results starting to move here. So let's see if I zoom in, if you might even be able to see. I know my camera hasn't been great at focusing, but you should see that our temperature gauges are turning from black, right, just like a moon ring, and they're starting to change color. Now, is anyone able to tell, maybe if I turn my camera up just a little bit, which one is conducting the heat the fastest? Is it the steel, the brass, the aluminum, or the copper? Zoom back in. Which one is the best thermal conductor based on what you can see? Yeah, that's right, the copper. The copper is by far the best thermal conductor. So it is the best at taking the heat from the hot water and transferring it or allowing it to flow through this metal. So copper is a great thermal conductor. It's also a fantastic conductor of electricity as well. Our steel, not so great, right? Not great at conducting thermal energy, but that can be very beneficial, right? If we think about things that we build, right? What about things that we build that we might need to touch? We don't want to build things out of really thermally conductive materials because then they might become too hot to touch very quickly. So steel, right, is a much better alloy to make things out of because it won't get super hot. It's going to resist that change in temperature. And so this one actually feels very, very cool, whereas the copper feels very, very warm from being inside that hot water. So I know I am almost at the exact end of our time together here today. I have no more experiments left to show you today, but I will make sure I send materials list to Molly and Katie. if you'd like to try this experiment at home, this thermal conductivity, there is something very easy you can do. All you need is a tray of ice cubes, and then you can just test different materials. So I had an aluminum block and a plastic block. You could pick two different types of plates in your home, so maybe a glass plate versus a plastic plate versus a paper plate, or you could choose different cups. So pick some different materials and see how well you can get them to melt ice. The one that melts it the fastest, right, is the best thermal conductor of heat. So that is all I have. I see Molly and Katie have popped back in here. If you guys have any questions before we head out today, I'd love to answer them.
There was one just before the students started popping the copper answer in. So Charlotte and Isaiah wanted to know, why do we have metal cooking utensils then if they can become hot?
That's a great question. Now, we use them for different purposes, right? So it depends on what you're using them for. A lot of things, like I know my barbecue tongs are made of metal, but they have a plastic or high density foam handle on them, right? So the part that you touch, if it's something that is designed to be used near something that's hot, like your barbecue or over a boiling pot of water, they normally will have a plastic handle on them to keep your hand from getting burned. We can use other metal utensils because they're actually very hypoallergenic. So they actually stay clean. So wooden utensils can actually grow bacteria on them. So there's benefits to using metal. Copper is actually one of those things that's antimicrobial. So bacteria and viruses actually can't grow on the surface of copper, which makes them great for things like cooking utensils, like pots, things that we use for food. But they do get very, very hot. So there are benefits to using metal, but there are also detriments, or there's pros and cons, right? So we don't want to use wood, but wood is definitely safer for us to touch.
Right. So often you can see a copper pot with a fancy wooden handle. So that's the way they would handle that. And Kerrigan said that was a great session. Thank you. I love how the students always thank our presenters. That was so great to be able to learn some experiments that we can do at home. And those are ones that we can do outside now too, now that it's getting nicer a little. Well, maybe not for Rael, not yet, but it will get nice, Rael, soon. And we will see Miss Anna next week. I forget what's up, but something cool is always happening. And